heat engine operating between energy reservoirs of 20 degrees Celsius and 600 degrees Celsius has 30% of the maximum possible efficiency. How much energy must this engine extract from the hot reservoir to do 1,000 joules of work? So they tell us that E max is equal to, or the E is 30% or 0.3 of E max. And so we don't know this right now. And then they tell us that the it's operating between two temperatures. So temperature for cold is 20 degrees Celsius, which is 293 Kelvin, and T hot is 600 degrees Celsius, which is equal to 873 Kelvin. Okay, so let's figure out what the actual maximum theoretical efficiency is. So E max is equal to 1 minus TC over TH. So when we plug everything in, that gives us 1 minus 293 over 873. So that gives us an E max of 0.664 or 66.4% is our theoretical maximum efficiency. Now let's go through and figure out what the actual efficiency is. They tell us that E is equal to 30% of E max, and we just solve for E max as 66.4%. So the actual efficiency is 0.3% efficient of 0.664, and that gives us 0.1992 or 0.2, or in other words 20% is our actual efficiency. Now we want to know how much energy must this engine extract from the hot reservoir to do 1,000 joules of work. So now they're saying that we want 1,000 joules of work, and we know that the actual efficiency now is 0.2. So let's use the efficiency equation of E equals work over Q hot. So now if we times both sides by QH, and then we divide over E. I'm going to move this down a little bit. So let's rewrite it down here. So now we have QH is equal to work over efficiency. So now that gives us 1,000 joules divided by the efficiency, which we just figured out was 0.2, and that gives us, I actually did the non-rounded version of this, so I'll do that just so you can see my numbers. So I did 0.1992 instead of the rounded 0.2 efficiency. That gives us 5,020 joules is Q hot, or rounded is 5,000 joules.